All right, let's get right into it. We're basically swimming in data, right? Polls, stats, averages, they're everywhere. But how do you actually make sense of all the randomness? Well, it turns out there are two, let's call them fundamental laws of statistics that help us find that order in the chaos. And we're going to break them down right now. So, have you ever noticed this? Think about one of those guess how many jelly beans are in the jar contests. It's a classic for a reason. One person's guess might be way off, but the average of everyone's guess, it's often shockingly close to the real number. So why does that happen? It's not magic, it's math. And yeah, the answer to that puzzle lies in two of the most powerful and I think really beautiful laws in all of statistics. These are like the twin pillars holding up our understanding of everything from coin flips to, you guessed it, political polling. Let's start with that first idea, that intuition. People often call it the wisdom of crowds. It's a great concept, but let's put a proper name to it. This is the law of large numbers, and the core idea is actually pretty simple. The more independent samples you take, and independent just means one guess doesn't influence the next, the closer your group's average gets to the real average. With more data, you are literally homing in on the truth. You can really see this with the simplest example possible, a fair coin. We all know, in theory, the probability of heads is 50-50, or 0.5. But in the real world, how many flips does it actually take to get close to that? Okay, let's see. With just 10 flips, you've got about a 66% shot of getting a result somewhere between 4 and 6 heads. That's not bad, but it still means there's a 1 in 3 chance you get something more wild, like only 2 heads, or maybe 8. But now, look at that jump. Bump it up to 100 flips, and the probability of landing in that same 40 to 60% range, it skyrockets to over 96%. See, all those random individual flips, they start to cancel each other out, and the true 50-50 nature starts to shine through. And by the time you get to 1,000 flips, wow, it becomes a near certainty. You're almost guaranteed to get a result that's incredibly close to that true 50% average. That's the big takeaway. More data gets you closer to the truth. That is the law of large numbers in action. Okay, so that's law number 1. It's pretty straightforward. But there's a second law at play here, and honestly, this one's even more profound. It's not about where the average is going, it's about something else entirely. So, the average gets more accurate as you get more data. Got it. But what if we did our 100 coin flip experiment, say, thousands of times over, and then we plotted every single one of our results on a chart? What shape would that graph make? This is where things get really, really cool. This is the central limit theorem, or the CLT, and it's basically the magic trick of statistics. It says that it doesn't matter what you start with. It could be a weird, lopsided, totally flat set of data. If you take enough samples from it and average them, the distribution of those averages will always, and I mean always, form that perfect, beautiful bell curve. Let's actually watch it happen. Imagine we have data that's just completely flat. Every single outcome is equally likely. A total mess. But as we start taking the averages of more and more samples from this, look at that. A bell curve just emerges out of the chaos. It's incredible. Okay, what about something really strange, like this skewed distribution where most of the values are small and there's a long tail? Well, it doesn't matter. We start averaging the samples, and there it is again. The same perfect symmetrical bell curve appears. And this even works with our coin flip, which only has 2 possible outcomes. As you increase the number of flips in each of your samples, the plot of the possible averages fills in and smooths out into, you guessed it, a normal distribution. This universal pattern is the absolute heart of the central limit theorem. So this is a cool math trick, but why does it matter in the real world? Well, this incredible piece of mathematics is the entire foundation for something we see all the time, political polling. I mean, think about it. You might have 150 million voters in a country. A pollster goes out and talks to maybe 1,000 of them. The difference in scale is just mind-boggling. So the obvious question that everyone asks is, how on earth can a tiny sample of 1,000 people tell you anything meaningful about a population of millions? How is that not just random noise? Well, the answer is the central limit theorem. Here's how it works.
First, the pollster takes their random sample of 1,000 people. Now, the CLT tells us something amazing. Their result, let's say 52% support for a candidate, is just 1 point on a giant, invisible bell curve of all possible poll results you could have gotten. And because we know the exact shape of that curve, we know that about 95% of all possible polls will be really, really close to the true answer. That predictable range of closeness is what we call the margin of error, which for a sample size of 1,000 usually works out to be about plus or minus 3%.
Okay, let's pull all of this together. We've talked about two huge, powerful ideas, so what's the ultimate takeaway here? Here's the simplest way to think about it. The law of large numbers tells you where your average is headed, straight for the true value. The central limit theorem tells you the shape of all the possibilities around that truth, a predictable bell curve. So one law points to the destination, and the other gives you a map of the surrounding territory. And this is exactly why the CLT is such a game changer in the real world. As Orloff and Bloom from MIT put it, the theorem lets us use that reliable bell curve as a shortcut. The math behind that curve is so well understood, it makes incredibly complex problems suddenly become solvable. But here's the final thought. The central limit theorem gives us confidence, but it doesn't give us certainty. It lets a pollster say they're 95% confident their result is within the margin of error. But that leaves this one nagging question. We know that about 1 out of every 20 polls will, just by pure random chance, be one of those outliers from that other 5%. So how do you know if the poll you're reading right now is one of the lucky ones or not? That's something to think about.